So in our last chapter that we're going to cover, we're going to talk about the logarithmic, exponential, and some other transcendental functions. So mostly we're going to be talking about inverse, trig functions in combination with these. So we'll go through the process for differentiating, we'll go through the process of integrating, we're going to talk about inverse functions as well, so we'll see a nice combination of everything. Now I am going to kind of go a little bit astray from the book, so it doesn't talk about inverse sections until section 5.3, but you have dealt with these in both your college algebra and pre-calculus course, so I know you've seen most of this material, and I'm going to kind of use that to our advantage to show you where stuff comes from. So we're going to begin by going through the natural logarithmic function, and we're going to start just with differentiation. So the first thing you want to remember is about our exponential function. If you have 3 to the x, that's an exponential function because that variable is in the exponent. And remember, when you're dealing with exponents, if you have a positive integer, if I take b to the n, it just means you're taking b and multiplying it by itself n times. So that's one of our exponential properties. Also, if you take b to the 0, so any base to the 0, it equals 1. If you have a base to a negative exponent, you can make it positive by flipping it. If you have a fraction as your exponent, you can go ahead and put this inside a radical, so it would be the qth root of b to the p, or you can switch that order, take the qth root of b, and then raise it to the p power. That's where these two values of p and q are integers. So in general, our exponential function is a function of the form f of x equals b to the x, where b is some positive constant. So based on that value of b, that tells us what the shape is going to look like. So we have 3 different cases. It is a positive number, so your base could be between 0 and 1. Your base could be bigger than 1, or your base could be exactly equal to 1. So we're going to look at the case the base is greater than 1 first, because that's a little bit easier to think of. If you think of 3 to the x, 3 to the 100th power is ridiculously large. 3 to the negative 100th power is 1 over 3 to the 100ths. So it's going to have this kind of shape overall. And if you plug in 0, b to the 0 is going to be 1. So we're always going to go through 1 as our y-intercept. If you have a fraction as your base, like 1/2, 1/3, 2/3, anything like that, it's going to have the exact opposite shape here. Because if I take 1/2 to the millionth power, it's microscopic. But 1/2 to the negative a millionth flips that, so it grows larger as x gets negative. So it's the exact reverse. If your base is equal to 1, then you really just have a flat line. So this is going to be super, super, super boring for us. We are not going to consider that possibility. Our base is going to be some decimal between 0 and 1, or it's going to be bigger than 1. Okay? But the thing that's really important in all of these situations, the domain is from negative infinity to positive infinity. The range is from 0 to infinity. So if I take a positive number and I raise it to an exponent, I'm never going to get something negative. I also never actually have that exponent giving us something that equals 0. Okay. So let's take a look at some of our exponent laws that we've used pretty frequently. If a and b are positive numbers and x and y are real numbers, then the following properties hold. First is if you take two things that have the same base and they have different exponents, or even the same, you go ahead and add the exponents. If you divide two quantities, you go ahead and subtract their exponents. If you take an exponent to another, you multiply them. And if you have two different values raised to a power, as long as they're being multiplied, you can distribute that to a to the x times a to the b. You want to be careful if that was addition in the middle, you cannot distribute it down. It only works if it's multiplication or division on the inside. So here's where I'm going to use a little bit of your knowledge about functions that you've dealt with in almost all of your classes beforehand. Because this exponential function passes the horizontal line test, we know it has an inverse. So that's what we use to check whether something was 1-to-1. We're going to dive into this a little bit deeper in section 5.3, but we're going to utilize your knowledge. You've seen this before to go through it. So basically, if I have this exponential function y equals a to the x, it has an inverse, and remember, it means those roles of x and y switch. So this logarithmic function is equivalent to saying, if I take log base a of y, it's going to give me x. So basically, the output of my exponential becomes the input of my logarithm. The base of my exponential is the base of my logarithm. And then here, this was the input for my exponential. It is the output for my logarithm. Okay? And then since these are inverses of each other, we know that their graphs are reflections about the line y equals x. So if we take a look at our two cases with our base being greater than 1 and our base being less than 1, but positive, we can go through each of those possibilities for this graph. Okay? And so we deal with that line y equals x when we talk about inverses. And again, we will see why that's true in a few sections. Okay? But for our exponential function, it goes through the point 0, 1. The base is bigger than 1. It looks like this. So that's y equals b to the x. We have our point here at 0, 1. When you flip that, it goes through the point 1, 0. And the graph instead will have this reverse image. So this is what log base b of x looks like. In the case we deal with a base being between 0 and 1, it still goes through the point 0, 1, but has this shape overall. So this is our exponential function. If I flip that point, my logarithmic function still goes through 1, 0. But when I reflect it, it has this shape instead. So this is our logarithmic function with base b. So ultimately, if we know all of these properties about the exponential function, we can get our properties for the logarithmic function. So we're going to go through all of those classifications. Thinking about our exponential function, you can input whatever you want, but your range is from 0 to infinity. Because these roles switch, we go ahead and switch the roles of the domain and range for the logarithmic function. So for logarithms, my domain is from 0 to infinity. My range is now all real numbers. For the exponential function, our y-intercept is 0, 1, but we do not touch the x-axis. Now again, x and y switch, so these are closely related, but they're not exactly the same. Now though, I do have no y-intercept, and this point really kind of comes down here, but remember x and y switch, so we're going to flip that coordinate pair. My x-intercept for the logarithmic function is 1, 0. For exponential functions, we also do have a horizontal asymptote. We do hug the x-axis. So ultimately, the x-axis is our horizontal asymptote, and we have no vertical asymptote. Again, these flip-flop. So now we have no horizontal asymptote, but we do have a vertical asymptote. And so again, x and y switch. Now it's going to be x equals 0 or the y-axis as our vertical asymptote. So the two things you really want to pick away is you cannot take the log of a negative number because that domain is from 0 to infinity. So if I have a function inside my logarithm, to find the domain, you need whatever that inside argument is to be positive. So i.e., if I've got a function inside my logarithm, we need that function to be greater than 0. The other thing you want to remember, again, using kind of just your base knowledge of inverses, if you take a function and evaluate it inverse, it cancels out. So if I take the exponential function, evaluate it at that logarithmic function when they have the same base, it cancels out. So I just end up with x. But this is only true if x is greater than 0, because otherwise we have a problem in here. If you do the reverse, and if I take the inverse, evaluated the function, those cancel out. So if we evaluate the logarithm at the exponential, these are inverses of each other. So again, those cancel out and you get x. But now you have no problems because you could input whatever you want into that exponential. Then also, using our properties of exponential functions, we get properties of logarithmic functions. So if x and y are any positive numbers, when we're dealing with a logarithm of multiplication, we can go ahead and split that as the log of the one piece plus the log of the other. If we're dealing with division, remember division in terms of exponentials equates to subtraction, we go ahead and subtract the log of the numerator minus the log of the denominator. If we have an exponent, think of that as repeated multiplication, so x times x times x times x. You would go ahead and ultimately add all those up, so that exponent is going to pop out because it would be log base a of x plus log base a of x plus log base a of x. And you do that r times, so the exponent comes out from. Now we have a really important base that is that natural base. So we've used that number e before. It's about 2.718. It's just a number just like pi is. It's known as the natural base for that exponential function y equals e to the x. And then corresponding to base e, we have a special logarithmic function that's called the natural log. Instead of writing log base e of x, we're going to write ln to stand for natural log. So what we're going to do is, you've seen this number before. It's really special because it has a special definition. So what I want to do is I want to go through the derivative of exponential functions specifically with this base e. So I'm going to show you in general what it looks like, but then give you where this definition of e comes from. So we're going to let f of x equal a to the x. Using our definition of a derivative, remember f prime is the limit as h goes to 0 of f of x plus h minus f of x over h. Utilizing, this is the exponential function, evaluating it x plus h gives us a to the x plus h minus a to the x, and then divided by h. One of our properties is when we're adding those exponents there, you can break that apart as multiplication. So it's typically the reverse that you've seen, but no problems going the opposite way. A to the x plus h, you can write as a to the x times a to the h minus a to the x divided by h. Now, both of these pieces have an a to the x in common, and that has nothing to do with this limit, so I can pop that out front. So I get a to the x, and what's left over then is the limit as h goes to 0 of a to the h minus 1 divided by h. And so we're really going to take a deeper look into what this quantity is, because it is a special limit. So think of that, a to the h is the same thing as a to the h plus 0. 1 you can rewrite as a to the 0. And that is specifically the derivative of the exponential function evaluated at 0. So kind of just looking back up here, it's like we've plugged in x is 0. So what this means is f prime of x for the exponential function is really the exponential function times the rate of change at 0. So the rate of change of any exponential function is really just proportional to itself. Now the number e comes from making this something super specific. So e is the number so that this limit, which is the derivative evaluated at 0, ends up equaling 1. So ultimately that gives us one of the nicest derivatives for the natural exponential function. But the problem is that doesn't work for every exponential function. So we'll see how to handle bases later on. But basically what this means is we've got this exponential function. You need the derivative evaluated at 0, which would give you the tangent line at 0. So this number e is defined specifically so the tangent line has slope 1 at this specific point. And that ultimately tells us the derivative of the natural exponential function is just itself. So we've made it so that this piece is 1. The derivative of e to the x is exactly e to the x. And then we'll get some type of proportion that happens for other bases, but again, later on. Okay. So let's get some practice using that. Given the function f of x equals 2e to the x minus 14x, we're going to find the first and second derivative. So to go and find the first, if we take the derivative of 2e to the x, it's the nicest thing, it is 2e to the x. Derivative of negative 14x is negative 14. To find the second derivative, again, I go ahead and take the derivative of each. Derivative of 2e to the x is again 2e to the x. Derivative of 14 is 0, so this is our overall second derivative. All right, so let's go ahead and now utilize this to find the derivative of just the natural log function. And so we want to derive y equals the natural log of x. Problem is that's a lot more complicated to go through. So what we're going to do is actually utilize implicit differentiation. We're going to see how that's helpful for us. So what we want to do is we want to convert to exponential form and then take a derivative that way, knowing the derivative of e to the x is e to the x. So dealing with y equals ln of x, this is equivalent to saying e to the y equals x. So remember, just convert this to its exponential form. Its base is e. The input of the logarithm becomes the output of the exponential. The output of the logarithm is the input for the exponential. So those roles change. So if I want to take a derivative of this quantity and find y prime, I'm really going to work with this piece instead. So taking a derivative with respect to x gives us the derivative with respect to x of e to the y is the derivative with respect to x of x. Now, these are different variables, so thinking of our implicit differentiation, derivative of e to the y is e to the y, but you get that y prime attached from the chain rule. On the right-hand side, those match up, so we don't need to worry about that. The derivative of x is 1. Okay. This is the quantity I want to solve for, so what we can do is go ahead and multiply both sides by 1 over e to the y. So like we're dividing by e to the y. That ultimately gives us y prime is 1 over e to the y. But I want my derivative to deal with x. I've got y prime, I've got y as a function of x. My derivative better be a function of x. So what we can really notice here is I've got e to the y in the denominator. That's just x. So ultimately, y prime is 1 over x. So for the natural log function, the derivative of ln of x is 1 over x. So both of these have really nice properties, and this is that missing case we were dealing with before. We couldn't find the antiderivative of 1 over x using that reverse power rule because it posed a problem when we would bump the power up from -1 to 0 and then divide by 0. So this is why it really is the derivative of the natural log function. So let's go ahead and try some examples. We're going to differentiate the following functions, and we're going to start with y equals natural log of x times cosine of x. So we have the product of two functions. Got to go through my product rule. So y prime is the first times the derivative of the second plus the second times the derivative of the first. Derivative of the cosine function is negative sine, so this becomes negative natural log of x times sine of x. Derivative of the natural log of x is 1 over x, and then we times that by cosine of x. If we go through the derivative of y equals natural log of x cubed plus 1, we really need to use chain rule because it's not just x on the inside. So thinking about the derivative of the outer function, it's 1 over x, but it has to stay evaluated at x cubed plus 1. So ultimately, y prime is 1 over the inside. Chain rule tells us we then have to multiply by the derivative of x cubed plus 1. And that's just 3x squared. So really, you could put 3x squared in the numerator, x cubed plus 1 in the denominator. So really, in general, combining that chain rule with the natural log function tells us if we take the derivative of natural log of a function, it's 1 over the function multiplied by the derivative in the inside. So ultimately, you get f prime over f. Okay. So we're going to get a lot more practice because we're going to go ahead and find antiderivatives of these. Like I said, we're going to do other bases, so we'll get a ton more practice finding derivatives, but at least it's a start for now. What we're going to do in the next section is now utilize the fact that we have the derivative to go ahead and find the integral of these.